Hello everyone and welcome to my presentation on deciphering the role of representation disentanglement investigating compositional generalization in clip models. My name is Reza and today I will walk you through the key findings of our study, which investigates how clip models perform in compositional out of distribution scenario. Okay, let's start with a quick introduction to CLIP, a model that developed by OpenAI that connect image and text. CLIP was trained on a massive dataset, over 400 million pairs of image and text using contrastive learning. This large-scale training allows CLIP to have a great generalization. Despite its success in handling out-of-distribution cases, compositional generalization, the ability to handle new combination of known concepts, remains a challenge. Our work addressed these by evaluating CLIP's performance in the scenario of combination of the objects and attributes using our ImageNet-AO datasets, which I will discuss next. Existing datasets often fail to provide true compositional out-of-distribution scenarios. Many benchmark datasets are biased toward familiar object-attribute combinations that were likely encountered during training phase. This is where our work contributes by creating ImageNet-AO dataset, which introduced truly novel combinations for CLIP to evaluate. Now let's talk about the process behind building ImageNet-AO dataset, which is a central part of our work. The goal of this dataset is to create a benchmark that challenges CLIP's ability to generalize new combination of known objects and attributes, something that existing datasets don't fully address. To achieve this, we begin by selecting a diverse set of objects and attributes, combining them in a way that they are unlikely to have been encountered during CLIP training. These combinations were then used as a prompt for generating images with the Stable Diffusion model. However, simply generating the images wasn't enough. We implement a careful filtering process to ensure that images accurately represent the object attribute combination and were truly novel. This involved manual check as well as something like similarity search to ensure that uniqueness of these images. You can see some examples of our datasets in this slide. Okay, after that, using ImageNet-AO, we compare various CLIP models trained on different datasets. Our dataset is compositional out-of-distribution for these models. Our findings reveals that model trained on a larger and more diverse datasets like Lion and Datacom exhibit better generalization to new compositions. However, we also observed that dataset size alone isn't enough. The quality and curation of the data plays an important role. As you can see, some models that train on a smaller dataset has a better performance than the models that train on a larger datasets. Okay, why CLIP has compositional generalization? We use various metrics to evaluate the level of disentanglement in both text encoder and image encoder. Our results showed that the more disentangled models representation are, the stronger is performance in compositional out-of-distribution generalization. Additionally, we observed that the level of disentanglement is generally higher in the text encoder compared to the image encoder. Based on this, we proposed that disentanglement in text space is transferred to the image space through the CLIP contrastive loss. To examine this claim, we trained a CLIP model and evaluate this disentanglement at different epochs. As expected, we found that the text encoder exhibits higher disentanglement from the beginning, while the disentanglement in image encoder gradually increased through the training process. Thank you for watching. If you would like to learn more or access our datasets, please check our paper and the GitHub link in that paper.